We will talk about failure mode effect and criticality analysis in another video or two. But first, though, I want us to go through with a general overview of the theory behind calculating a quantitative criticality number. Criticality is a rating of how bad the outcome is when something goes wrong. If you remember way back to PowerPoint number 2, we discussed system attributes. One of the system attributes was system domains. One of the domains was system complexity, and one of the elements of complexity was just this, criticality. Understanding criticality, it's deep within the system attributes, but understanding criticality can help us to prioritize hazard mitigation strategies. For FMECA, there are several methods to use. In your presentation, we discuss two of the more popular methods in this unit. First, a quantitative technique called failure mode criticality number. That's what we'll talk about here first. The formula for failure mode criticality incorporates actually 4 different elements. Here are 3. We'll get into the 4th momentarily, but mode criticality equals expected failures times the mode ratio of unreliability times the probability of loss. Let's look at each of those 3 components here in more depth. Expected failures. That's the first element of the equation. This is the number of failures at a given operating time. It is not time dependent. For example, it is not a failure of 2 per 500,000 operating hours. Expected failures are actually base failure rates, and they're obtained from handbooks and reference material that are then adjusted, increased or decreased for operating stresses that are particular to your environment. So the expected failure or part failure rate is one element of the failure mode criticality number calculation. It can be adjusted for different factors, application factors, environmental factors, and other factors that would increase or decrease that part failure rate number. The next element of our criticality equation is the failure mode ratio of unreliability. The failure mode ratio of unreliability provides an indication of the chance the failure will occur in that particular identified mode. It's expressed as a decimal fraction, and the sum of all the values for the identified part or item will equal 1, or 100%. That failure mode criticality number is another element, that second element in the failure mode criticality number. Probability of loss, the third element in our equation, is the likelihood that the failure effect will result in the identified criticality classification. In other words, will it result in actual loss, probable loss, possible loss, or no loss? Probability of loss, that's the third element in our criticality number calculation. This fourth element, exposure. Exposure or operating time is the fourth and final element in the criticality number calculation. And exposure relates to how long the mission is, how long is the duration, or how many cycles will it have to go throughout the life cycle of the mission. The failure mode criticality number then is the product of all 4 elements that are previously discussed. The probability of mission loss, the ratio of failure mode, the part failure rate, which is, remember, obtained from other data, adjusted for your particular application, and then the exposure, finally, or the duration of the mission. MIL STD 1629A provides a criticality worksheet for documenting the elements of the criticality number calculation and analysis. In the next video, we're going to get into an alternative, a little bit less technical way of quantitatively measuring criticality to help us prioritize risk mitigation strategies. The next technique that we're going to talk about is called the risk priority number, or RPN.